All right. So we did acid-base titrations. Now we're going to do EDTA titrations. So EDTA, yay. So EDTA is ethylene diamine tetraacetic acid. If you look at that name, it kind of gives you an idea what this is, right? It has an ethane, has 2 amines on it, and then it has 4 COOHs, right? Cool. This is a compound that forms a strong 1-to-1 complex with most metal ions. As we'll see, it actually is a chelating agent that grabs onto those metals and holds them real tight. Okay? This is used in many industrial processes. It typically gets used in things like detergents, cleaning agents, food additives. This prevents metal catalyzed oxidation of food as a additive for foods. The metal EDTA complexes find their way into the environment because they typically pass through the wastewater treatment plants unscathed. There's not really anything targeting those. So, which I guess would actually undo some of the like lead and metal ions we probably put in the environment. I wonder how much of the pollution is undoing other pollutions we do. Anyways. So the metal ions are going to be Lewis acids. They accept electron pairs from electron donating ligands, which will be Lewis bases. Monodentate ligands would bind to a metal ion through only one atom. For example, this would be things like CN minus, right? This would be things like your OH minus. Those are the ones you're probably most used to, right? So you have one group that binds the metal ion that's monodentate, literally one-toothed, okay? That's literally what that means, by the way. Think of them as like Pac-Man or something. They're biting. And so these only bite one place, okay? Monodentate. This would be didentate right here, and that's you're seeing an example of, where it's binding in 2 places, right? Or multidentate, multiple dentate, multiple toothed, biting in more than one. So anything that binds a one ligand atom more than once to a metal is a multidentate or a chelating agent. So again, a ligand that attaches to a metal ion through more than one ligand atom is going to be multidentate, literally multi-toothed, right? Did you guys have inorganic at all? This is typically what's referred to as inorganic chemistry that we're going to dive into a little bit, okay? We'll just touch on it. There is more to inorganic chemistry than this, but yes, this is part of inorganic chemistry. That's very important for that. This is also very important for enzymes, by the way, as we'll see in a little bit. Chelating agent literally means cutting agent, okay? Chelating literally means to separate, cut. Which if you wrap up a metal, it's going to cut it off from everything else, right? It won't allow the other ligands to get to it. So ethylene diamine here is a simple chelating agent that is a bidentate. See that? Two-toothed bidentate. The chelate effect is the ability of a multidentate ligand to form more stable metal complexes than those formed by similar monodentate ligands. Literally, in a chelate effect, you're going to bind that metal and it's going to separate those from the other ligands, right? And it does that because, well, entropy would actually be part of that. You have one molecule being used to make your complex versus 2, right? So you have an entropy effect. And it will also do it due to steric effects as well. So this reaction right here, here we see the, oh, I don't have it, do I? Anyways, here's a metal with 6 waters. So those are, each of those waters would be monodentates, right? You have 6 of them taking up the cluster around that metal, right? And we're all kind of familiar with that by now, hopefully. Okay? All right, so you can actually bind that with 2 ethylene diamine. This is going to be more favorable than having all monodentates, because you can release those monodentates, there'll be more of them, and that will give you greater entropy for the universe, right? By the way, you guys notice what that is? It's ATP, isn't it? What do you notice ATP does here? Yeah, ATP makes complexes, metal ions. That's actually the active form of ATP, by the way. Without the metal ions, ATP doesn't work. All your enzymes can't process it correctly. So, your enzymes also require metal ions. That's why you have to have metals in your diet, if you're ever curious. And you start getting unhealthy if you don't have them in your diet. Yeah. So, ATP here, multidentate, right? 4. Okay, there's 2 waters, by the way, which also bind to the metal. By the way, different metal ions have different sizes and would actually change the geometry of the ATP and can actually cause enzymes to stop binding to their substrates. Kind of interesting, huh? It's something that a person I worked with used to do a lot of. He would use different sized metal ions to see if they block off different parts of the binding site of enzymes. And then he could tell, where that metal ion was and which groups were involved. Pretty cool. Okay, these are some different useful chelating agents. EDTA is probably the one we're going to be most familiar with by the end of this, because we'll use it a lot. But these are all quite useful chelating agents, and there are more chelating agents, but they are not typically as well used as these ones. These are some of the most common. Okay, so titration based on complex formation would be called a complex metric titration. I know, right? Isn't that just something you want to say fast 5 times? Okay. So EDTA would be the most widely used chelator in analytical chemistry to do these titrations with, because it's very stable, it's very easy to get your hands on, just works very well. These are typically done through a direct titration, but you can do them through an indirect series of reactions. Virtually every element of the periodic table can be measured with EDTA in some way or another, because you can make ions of essentially every element, right? All right, so EDTA is a hexaprotic system. It'd be designated, when it's fully protonated, it would be H6Y2+. 2+ coming from the amines, right? It'll have the positive charges. Okay. And so it has 6 pKa's for losing protons from this. The first 4 of them would be the carboxylate acids, right? See the carboxylic acids? Okay, there's 4 of those. Those would be the first 4 acidic pKa's. The 5 and 6 would be for losing the protons off of the basic parts, the amine. Once you have lost all of the protons, you'd be left with Y4-, which is the conjugate base form, right? Notice what pH would you want to get around to be in the Y4- form. You look over here, you'd assume something up in the pH 10-ish, right? Like 10.5, 11 should do it. See that okay? Okay. Fantastic. All right, so what is the fraction that is the Y4- form? Well, the fraction that's the Y4- form would be the concentration of the Y4- over all the other species, right? Another way of saying that would be the concentration of the Y4 minus over the total concentration of all forms of VDTA, which would just be, you know, concentration of VDTA is how you say that. All right, so the neutral acid is actually tetraprotic. It has the formula of H4Y. This can actually be dried at 140 degrees Celsius for 2 hours and can be used as a primary standard. So this is a primary standard that you can get, okay? And you can get it as a powder. The powdered form is typically this neutral form. Again, it's very difficult to make crystals as something that's charged, right? So typically have issues if you try doing that. All right, so this is the different, this is actually your pH versus fractional composition. This tells you the primary species at each pH level, okay? Notice this is an H6, so it has quite a few different primary species, right? All right, so as you go up, you pretty much get the behavior you'd think, which is you get down to Y4 minus after pH 10.5-ish. Everybody see that okay? Anybody have any questions about that? So like if I gave you one that's between pH 8 and 9, what's the primary species? Let's go here. Primary species is that one, isn't it? What other species do you have in that? You have the Y4 minus a little bit, and you have the H2, Y2 minus, right? Okay. Very little, right? Mostly Y3 minus. Is everybody okay with that? Where would I find a 50-50% H2 Y2 minus and HY3 minus form? At pKa 5, wouldn't I? Okay. Everybody seeing how to read this information? Okay. Have you guys seen one of these before? I think there was a little bit of it in your biochem, but we didn't really hit on it much. I think we kind of, you know, just this is what it is, and boom, we're done. These fractional composition diagrams actually give you a lot of interesting information and allow you to connect things you may not have connected yet. Like, for example, when you're at the pKa's, typically that is the point where we have 50-50, half-half, right? And you actually knew that from the Henderson-Hasselbalch, because pH equals pKa at 50-50, right? And so you need to actually get beyond by a unit or two for pKa to have, you know, a large majority of it being one species, okay? And this is actually that relationship that I gave you a formula of. Remember the, where you take the Ka's, Ka1, Ka2, and there's that square root of formula to find the pH between them. And you can get a number around the value by just taking 1/2 pKa1 plus pKa2. That's this right here. You see that? So the pH 1/2 between those, it's right there. Whoa, huh? Okay, again, the alpha here, that is the fractional composition that we were just talking about. So the alpha fractional composition for each species is the fraction of EDTA in that form. This would be the alpha Y4 minus right here. That would be the concentration of this species. That's the wrong one, isn't it? I think I got the graphic for the 3 minus. Anyways, your book probably has it right. God, I need to just, I'm going to have to get like a book scanner or something and scan your damn book and get the graphics myself, aren't I? Oh, man. All the graphic labeled that they sent me is wrong. All right. Remember that when you talk about concentration of EDTA, This is the concentration of all free, not complexed, EDTA species, okay? And so it would be the Y4 minus, the HY3 minus, all of those, okay? However, it is not the stuff that's complexed. The stuff that's complex would have the dot metal ion next to it, right? Okay. All right, this right here actually gives you the values for this composition at different pHs. See that? This is at 25 degrees Celsius with a strength of 0.1 molarity. You remember the ionic strength of this solution would change that, right? Change the activity. So again, this would be for those 0.1 or dilute solutions, right? All right, so the equilibrium constant for the reaction of a metal with a ligand, this is called a formation constant, it is a Kf. Another way of saying it is the stability constant. You can look at it either way. So you can look at it from the perspective of forming the complex or the perspective of the complex falling apart, right? In which case, stability constant or formation constant. That making sense? This is EDTA, by the way, the Y4 minus form, binding to iron here. Do note that these are coordinate covalent bonds typically. They are not hydrogen bonds, okay? Or dipole bonds or anything like that. They're coordinate covalent bonds, meaning they've literally taken the lone pair here and made a covalent bond with it. And that's typically what you experience, a type of ionic bond almost. It can slide into a covalent depending on the metal, okay? If you have things that are lower on the periodic table, they'll be more covalent in character. Okay, these are the formation constants for different metals with EDTA complexes. And you see here, like this is a fairly low values. Notice that they're kind of like pKs, but they're not negative. See that? Because it's a formation constant. So it doesn't have that reverse sign, right? All right. Notice that most of these are quite large, actually. See that? Most of them are like 10 to the 20 sort of things. 10 to the 10s, 10 to the 8s. Those are pretty big for formation constants, aren't they? And that's because EDTA tends to be a pretty good binder of any metal. It tends to be a larger, more positive charged cations will be better at binding it. You notice that this gets very large once it gets up to like V3+, which is both large and highly charged, right? We get very large values. See that? The small ones that are not very charged, we don't have as large values, do we? Still fairly large for most, Ks that you've seen, but not that large, is it? And again, remember that this is looking at larger is better at binding it, right? So most EDTA is not Y4 minus below pH 10.35 at 7, excuse me. At pH 10.37, half of the EDTA would be the Y4 minus form. Anything below that, the majority of it will be in the other forms. So the species HY3 minus and H2Y2 minus and lower would predominate at those lower pHs, right? So what we typically do when we use EDTA is we would fix the pH using a buffer system so that the alpha, the activity of the Y4 minus would be constant. This can then be combined with your Kf, and you can do the math then to figure out what your concentration of everything is that would bind it. Okay? It's very difficult to get the Y4 minus up to 100%, right? We would have to be in pH 12, 13. Those are very high pH conditions, aren't they? So this is called conditional formation constant. It would describe the formation of the metal and Y in -4 at any particular pH. And that's why we had that table. Remember the table I showed you? Right here? That's why we have that table. You can do it at different buffer regions. Different pH levels that correspond to a buffer. Okay? So the what time is it, by the way? Oh, okay. I need to stop. Let's stop here. We'll pick up next time. Now,